discuss the application of eigenvalues and eigenvectors. Let me review what we learned on eigenvalues and eigenvectors. So eigenvalue and vectors. I explained, okay, this is domain. Okay, so this is whatever one vector, x, right? When you apply a x, this is more or less, this outcome is b. This is a x equal b. It's like a function. On vector x, when you apply a, it becomes b, right? Okay? But this b may have its own length. Like in the case of this x, we already define this vector, right? So we can, this is more or less length plus what? Direction, right? This vector, right? Direction. So this b also becomes vector which have another length and direction, right? So in general, this is a relationship. But some vector here, some vector, okay? Some vector, whatever some vector here, is maybe whatever this x hat or whatever. Now it's b is almost like lambda x hat. It means for some selected vector here, when you apply a, oh, it's same direction result. Okay, scale will be different. Okay, that's what we call eigenvalue is lambda. Then we call them as eigenvector. Okay, that's the definition, right? Then how do you compute this? There are several different ways to compute. Then that's the definition, right? So we learned how to compute. First one is from A, we make applying row operation or elimination. We can make it triangular matrix, right? From triangular matrix, then all the diagonals is lambda, all the pivot. So that's one way. What's the second one? We say, okay, determinant of a minus lambda I, we just say a minus lambda I. This is the way we solve. Okay, this is determinant. So determinant is polynomial, 다항식. Like when, because this eigenvector is all defined all your square matrix. 이렇게 dimension n, this is nth order polynomial, right? Like when you're 2 by 2, this is second order, 3 by 3, third order, 10 by 10, 10th order. 2 by 2, you know how to solve it. 10 by 10, okay, we have to use computer, right? So when you use this one, sometimes you can say lambda 1, whatever this lambda, let's say n. Okay? Sometimes when you come to this lambda, sometimes these lambda's values are distinct. It means values are different. Let's say 1 or 2 or 5. But sometimes some values are repeated. Let's say, okay, there are 2, 6. 김상우, when is the case of when you have these repeated values? Can you give me some example of matrix which give you repeated values? Identity matrix, right? Identity matrix is like this is always 1, 1, 1, 1. Then when you apply that, it's 1 minus lambda, 1 minus lambda. This is more 1 minus lambda n, right? it's 0, right? So lambda 1 is eigenvalue. Then this is repeated values, right? This is polynomial. Sometimes it just multiplies 2 or whatever, right? So based on that, this third one is we use some property. Okay, I don't want to use that, but just by observing some matrix, we can compute. One of the properties is trace in the matrix. When you add up this diagonal, a trace is sum of lambdas. Okay, that's one property. What's the second property? Determinant, okay, of A is a product of lambdas. Okay, this is very useful property. For 2 by 2 matrix, actually you can compute it easily. Also another one is for singular matrix, lambda equals 0 is the 1, right? For singular matrix. Can you explain why? For singular matrix, lambda equals 0 is always the eigenvalue? Just reasoning. What's the concept of null space? Like in the singular matrix, null space is not 0, right? So singular, like, what is n over A? N over A is, solution is A, x is 0, right? We can multiply, not OX, 0 times x, right? In the case, lambda equals 0, this x is in null space, right, vectors, right? So when matrix A is singular, lambda 0 is the eigenvalue. Also, every vector in null space is an eigenvector. Okay? So there are 3 different ways. So when you use the property, sometimes you can easily find eigenvalues. Now you find eigenvalues. Then also I explained how you can find eigenvectors. Okay. When all these lambdas are distinct, we can find it easily. But lambdas are not distinct, sometimes you are not able to find enough number of eigenvectors. Okay. Okay. For each lambda I, okay, for each lambda I, right? Lambda I, A, let's say we find eigenvector, this xi. That means AXI is what? Lambda xi, right? So it means like AX1, whatever lambda 1, x1. AX2, lambda 2 plus x2. AXN is lambda n xn, right? We have n equation. Can you write this one as just one equation? Okay, AX1, AX2. Somehow, can you represent this one as just only one equation? Currently, we have n equation. Let's say this one is, can I rewrite it? Okay. Oh, this is one is more or less x1, x2, xn. Then this is one, you can say this is lambda x1 or lambda x2, whatever, lambda xn. think this set of equations are same as this? Kakujin, do you think so or not? AX1 is lambda x1, right? AX2 is lambda x2, right? So this is eigenvectors, right? Oh, okay. So we call this as an eigenvector matrix. We call them as eigenvector matrix. We just denote them as S. Okay? Then, okay, let's think about this. So AS, here is we explain, okay, AS is, that's the way we represent. This is the way we represent here, right? Also, this one can be rewritten again. Okay, this is more diagonal matrix, this is S. This is another representation, right? Oh, this is S lambda. So basically here what it says is S is eigenvector is S lambda. Lambda is diagonal matrix, right? It means A is what? S inverse. If S inverse exists, when does S inverse exist? When you, this one is correct, right? When you move from here to this, then this S inverse should exist, right? Otherwise, it doesn't make sense, right? So S inverse exists when all the columns are independent, right? So it means all the eigenvectors are independent. Then it's possible, right? Then, so A, now because, S lambda S inverse. Okay? So this is also one of the factorization. Okay, that's the one way. Or you can say, the other way is, this lambda, or you can say, this S inverse A S. Same thing, right? From S, now you find the eigenvectors, you can diagonalize, right? So, anybody has any questions on this diagonalizing matrix using eigenvectors? Young, can you understand that? Okay. Then we try to find some application to use that. Just remember A is S lambda S inverse. What is A square? It's A times A. This is like, no problem. Right? We can cancel this out, right? What's the multiplication lambda by lambda? Equal lambda square. It means each entry is diagonal, is squared, right? This is lambda square. This is lambda square. We just put this as inverse, right? This one you can easily compute because every entry diagonal will be squared. Then what AN? No problem. It's like it's pretty easy to follow, right? Okay? This is a property we're going to use when we solve difference equation. Okay? Okay. So this is what I explained to you. AK is SK. Then, okay, we're going to multiply this. Okay? If we represent this, actually, this one is more or less, let's say S times lambda 1 n, lambda 2 n, whatever, K, whatever. K, whatever S inverse, right? Okay. Let's say this is K. So it means when I say, okay, can you find 100s? Usually when you compute A 100 times, you should have many multiplication, right? A times A, again A, again A. You have to multiply again and again and again, right? When you have this relationship, well, no problem. I find S, I find this. Then, okay, for eigenvector, just this 100, 100, 100, that's it. Much faster, right? Then let's think of this limit. K goes to infinite. Let's suppose K goes to infinite. If each lambda is less than 1, absolute value, then this will disappear, right? Can you understand it? Then, like, if when K goes to infinity, the AK goes what? 0, right? Matrix of 0, right? Because all the values goes to 0, right? 박한서, can you understand that? How about lambda is 1? This always 1, right? How about lambda is greater than 1? This one will explode, goes infinite, right? So that's the property we're going to use. Okay? So try to understand what it really means. Okay, so I explained the procedure like here. Here's still now is if all the eigenvalues are distinct, different, then we can find n independent eigenvectors. Last time I just confused, right? It's not orthogonal, right? There's independent eigenvectors, right? Then each eigenvector, you can build eigenvector matrix. Then A is diagonalizable. Okay? Let's just discuss in the case of when for the repeated eigenvalues. Means like this is the case is lambda 1 is 1 is 1, whatever. Sometimes it's polynomial, sometimes some values are repeated. Okay. So in that case, sometimes we can find n independent eigenvectors. Sometimes we are not able to do that. Like in the case of identity matrix, right? This is lambda 1, lambda 2 is all 0, all 1, right? In that case, what's the eigenvectors in this case? What's the eigenvectors for this? For identity matrix. Eigenvalues, okay, that's easy. How about eigenvectors? It's identity matrix, right? When you multiply any matrix, it's X, right? It's identity matrix, right? It means any vector. Okay? Any vector. Okay? Sometimes when you say AX is 0, when you value 0, that means these eigenvectors are in null space. Okay? So in the case of identity matrix, okay, we can easily choose eigenvectors. Or you can choose from that, because you can choose any vector, but we like to choose n independent vectors. That's not difficult, right? You can just choose bases, right? This is another example at the bottom. This matrix is a matrix. When you compute that, then it's all the lambdas are 2. When you try to find eigenvectors, I can find 1, but I couldn't find any more. So in this case, you can only find 1. So even though lambda has repeated values, you are supposed to find 2, right? But you can find only 1. This is the area when you have trouble, okay? Let me discuss this. Then you move on to difference equation. Difference equation. What's the difference equation? What's the Korean translation? 점화식? 점화식 맞냐? You learn in high school, right? 점화식. 어떻게 푸는 거 배웠어요? 점화식? 응? 배웠어? 어떻게? 캐릭터리스틱 이퀘이션 풀고 그러죠. 그래서 이퀘이션 푸는데 왜 그런지 이해했어. Sometimes high school, you say, okay, this is a formula, you just apply it. Or this is procedure, you just do it. But I don't know why. Just he asked me to do it, right? You just follow it, right? Like obey your teacher, right? It doesn't have that much. Here we discuss how you solve that. Sometimes, for whatever reason, they say, okay, this is the way you can solve that, no problem. Like 학원 선생, okay, this is the way you solve it. They never say why it works. Okay? But difference equation, you know that. In the case difference equation, okay, you have only samples. Okay, this like from whatever n0, n1, or just go to infinite, right? So each time you just define values, then you try to find some relationship. Okay? This relationship let me ask a question. Have you learned of sorting in 창소설? Sorting? Okay. When you choose a sorting algorithm, right? You say, okay, I can choose this algorithm, that algorithm, or whatever. So from sorting algorithm, you try to find some computational complexity, right? What's the computational complexity of linear sorting? What is simple sorting? What's simple sorting? What's simple sorting? 김성, what's simple sorting? 네? let's say, just take example. This is 100 entries, right? One of the entries, right? Then first, find the smallest one. Let's assume this is the smallest one. Then compare this one, this one, this one. Just pulling out smallest one, right? Then okay, I find the smallest one. The problem is actually 99 entries, right? Again. Right? Okay, no problem. Then I say, okay. Another one is okay to find another one, right? 98 entries, right? This is a recursive function, right? So in that case, let's say when you have a computational complete time for n is, okay, t n minus 1 plus what? Any idea? How many comparisons do you make to have this? From here, to convert here, how many comparisons do you have? 비교 몇 번 해? You don't have to compare you against yourself, right? Okay? This difference equation, right? From here, then you say, okay, I like this closed form formula somehow. What's the closed form formula for this? Then once you again, then okay, this is, you just expand this, right? Okay, t minus n2, then minus, okay, a minus 2, a minus 1, right? Just go on, right? Reasoning, right? Then what's this? This one? Order of magnitude, right? This is, okay, this is order of what? N square, right? Can you understand that? This is the one, right? Okay. Then how about the merge sorting? How does it work when you merge sorting? It means like when you have like, let's assume you have like 100. What they do? What do they do? They divide up into 2, right? Okay, now it's problem 50 times 50. Okay, solve this. It means, okay, Tn or 2n, that's 2 times Tn plus, what's this here? When you merge it, how many comparisons do you need? 김상우. It's n of them or n of them. When you compare, how many? N. Okay? This merge. So problem just go down. Previous example just go on one less, right? This is more or less going down big, right? Half, right? Okay? Like in the case of 1024, then you have all this 1023, whatever. This one, 1024, 512, 256. So go down very fast, right? Okay? Based on that, this is more or less whatever n log n. But you have to solve this recurrence equation. Sometimes go down just one less, sometimes just jump faster or whatever. So this is, in general, this is a difference equation you have to solve. So, okay, that's the one case, but this case is different. Okay, this is just, so you have the concept of what the difference equation right? When they are used. Okay, so difference equation is, this is more vector notation. So UK plus 1 is 8 times UK. In this, all this equation was just for single number, right? Not for vector. Now actually, it's a U is a vector. This may be 2-dimensional or 5-dimensional or whatever vector. UK plus 1 is AUK. Okay? So, initially you start from whatever initial condition U naught. Okay? Then U1 is AU naught, U2 is A square U naught, then UK is AK U naught, right? Then once you serialize, yeah, it's U100 is 800 by U naught. But your problem is, how can I find this value, A100? Because once you are able to diagonalize it, then you can do much simpler way. Okay, once you diagonalize it, that means, okay, let's say K, here is AK U0. AK U0 was like S whatever, lambda K S inverse U0. So this one is, you can easily compute. Okay. Let's just try some use this. You know what the Fibonacci numbers, right? What's your Fibonacci number? Why is so famous? Why Fibonacci number is so famous? Can you explain why Fibonacci number is so famous? Yeah? Can you give some example? 예? 또 다른 하나는 응? 또 다른 거 뭐 있어요? 피부나치 남자. 예? 사람이 죽지 않는다고 가정을 하고 사람이 성인이 되면 해마다 애를 한 명씩 낳는다고 생각하면 어떻게 볼까질까? 그지? That's the origin actually. Yeah? So people never die, but when they are young, they cannot produce baby. But once you grow up, you can produce baby every year, in a way. Okay. So that's really what it is, right? Okay. So usually, okay, whatever 0, 1, 1, then 2, 3, 5, 8, or whatever. This was the initial condition, right? So here is actually what you want to compute is, can you find this F100? So anybody learned how to compute that? Fibonacci, I know that, but let's see how fast they can grow. Or somebody asks, can you give me like 100? Then just wait. I'll just compute from F0, 1 is given, right? Just compute. I'll come 2, 3, 4, 5, 6, 7, 8, 9, 900. Okay, I got it. But that's you can do, right? Are there any other way? Any other way? Okay, it's in mathematics. sometimes you are dealing with a sequence, right? You know what the sequence is, right? Like this. Whatever F1, whatever F2, whatever this Fn just goes on and on and on, right? This is okay, Fn is, but you know to compute Fn, can I ever really, you know what the closed form is, right? Yeah? If you give me a closed form, I can easily compute. I don't want to start from the beginning. You just say, okay, it's closed form, okay, you plug in the number, you got the result, right? That's what you want. Fibonacci number, yeah, no problem. You have 1,000, no problem. Just wait, okay? I'll just give you a number. Okay? So what really we are interested in what? We are interested in closed form. Okay? So this is formulation of this equation. So Fibonacci number it was just not vector, right? So here actually we define UK as a vector which is fk plus 1, fk. Okay? Let's put it this way. What is fk plus 1 is fk plus fk minus 1, right? Fk, can I say just simply Fk? Okay? So when I represent this matrix, is this okay? Kim Sang, is it okay? This is equation, this is just matrix forms, right? This one is okay. I got to define this as a k plus 1 is okay. I define this one is okay. I got to define this as UK. Okay. Then okay, UK plus 1 is whatever 1, 1, 1, 0, UK. Right? So by simply introducing this dummy equation, you can just have very good this form, right? You know, solve this, you need the initial condition, right? What's the initial condition? What's U0? U0, oh, U0, 0 minus 1. Oh, what's it then? U1. What's U1? In this case. Oh, U1 was, okay, F2, F1, right? This was the initial condition, right? Now, okay, from initial condition, then you can solve this problem. Okay, then no problem. Then what's the UK plus 1? Okay, UK plus 1. Somehow 1, 1, 1, 0, whatever. Case power U1, right? This is 1, 0. Okay? Once you are able to compute this one easily, you can compute that, right? So how can I compute this? We learned this one is okay using S, whatever lambda S inverse. Okay, K is K. Then once we find the eigenvectors, then eigenvalues, we can easily compute. Okay, that's what I just explained later. That's all I did, whatever this equation. Okay, for this matrix, I computed lambda. Okay, that was characteristic equation. Lambda square minus lambda minus 1 equals 0. So from there, I just find two of them. Strange enough, they have some square root. Okay, for each lambda value, I try to compute eigenvectors. Okay, then actually this is solution, bottom one. So, 지영탁, what can you observe here from this equation? C1, C2 you can compute like whatever using initial condition, right? Then this one, what's the second term? The value is around 0.618. So as n k increase, this will decrease, right? Will disappear, right? This one, value is 1.618, will grow. Then when it's large enough, this term will dominate. They say, okay, this is the approximate values, right? This is error terms in a way, right? So you can compute, okay, this is more or less grow with whatever exponential, whatever n. Right? This is value here, right? 자, 쇼트 한국말로 해봅시다. 지금 뭐 제가 무슨 짓거리 한지 알겠어요? 예? 김상우, 내가 무슨 얘기한지 알겠어요? 우리가 지금 이제 팩토리에서 A가 S 람다 S 인버스인가? 돼 있잖아요, 그죠? 이걸 통해서 AK는 S 람다 K S 인버스다 이렇게 돼 있잖아요, 그죠? 이걸 이용해서 그동안에 우리가 S하고 람다 구하는 건 다 배웠잖아요. 얘기를 해서 이거 갖고서는 디퍼런스 이퀘이션을 푸는데 보니까는 UK는 벡터로 보면 뭔가 A에 뭐 K에 U not 이니셜 컨디션이더라. 이걸 보니까 이거는 S 람다 K의 S 인버스라. 이걸 푼 거예요. 그러니까 이런 경우에 디퍼런스 이퀘이션이 익젝트 밸류도 구할 수 있고 장기적으로 n이 증가할 때 그 아심토틱 비헤이비어라고 그러나? 우리말로 뭐라 그래요? 예? K가 밸류가 쭉 증가할 때 어떤 형식으로 이렇게 되는지 그걸 좀 구한 거거든요. 그래서 나중에 n이 클 적에 밸류가 뒤에 텀은 굉장히 작아. 이 뒤에 텀은 굉장히 빨리 없어지잖아, 그죠? n이 100일 때 값이 얼마냐? 그러면 앞에 것만 계산해서 얼마다 이렇게 얘기할 수 있는 거지, 그지? 무슨 말인지 알겠죠? 그래서 이런 식으로 전부 다 구하는 거니 이걸 보면서 이게 어떤 식으로 익스펜드 하나 이렇게 볼 수 있는 거거든요. 그러니까 이제 어느 아까 식으로 얘기하면 인구가 어떤 식으로 늘어나냐는 걸 볼 수 있는 거잖아요, 그죠? 지구상에 저 인구 관리 안 하면 100년 지나면 사이클 지나면 저렇게 되겠네 이렇게 보는 거지, 그지? 무슨 얘기인지 알겠죠? 그럼 쥐는 뭐 1년에 12마리 난다. 그럼 12마리 나면 어떻게 되지? 이퀘이션 만들어서 구하면 얼마나 빨리 간지 드러나는 거지, 그지? 10년 후면 어떻게 된다 이렇게 드러나는 거잖아요. 그래서 멀티플라이 하기 힘들잖아. 무슨 얘기인지 알겠어요? 그래서 그런 개념으로 이거를 보시면 될 것 같아요. 그래서 지금 이제 K가 무한대 가면은 이런 식으로 비헤이브한다. 이렇게 보는 거고요. 이걸 하기 전에 제가 이제 약간 좀 빼먹은 게 있는데, 그래서 이제 제가 이걸 우리말로 할게 푸는 방법이 이래요. 이제 이게 푸는데. 우리가 아이겐벡터 매트릭스를 했잖아요, 그죠? 아이겐벡터 매트릭스는 무슨 개념인지 알잖아요. 이제 S1 이렇게 쭉 있잖아요, 그죠? S 있으면은 우리가 거기서 왜 초기 조건을 U0를 놨잖아요. 그죠? 예? 그냥 한번 생각을 해보자고. 지금 U0가 여기서 뭐 어떤 그 이렇게 스페이스에 어떤 벡터 아니에요, 그죠? 예? 벡터고 이게 아이겐 벡터가 n 디멘전을 인디펜던트 하면 김상호 베이스 쓸 수 있어 없어? n 디멘전에 이 S1에서 Sn까지 아이겐 벡터가 전부 인디펜던트 하거든? 람다 밸류가 다를 때, 그지? 그럼 베이스 써도 되지. 그럼 여기서는 n이 벡터, B는 이거 C라고 합시다, 표현을. 이런 식으로 표시할 수가 있지, 그지? 예? 유제로도 이렇게 표시할 수가 있죠, 그죠? 다 이 표현이에요, 그죠? 그렇지 않나? S1, C1 이렇게 해서, 그죠? 베이스로 된다는 얘기가 이 안에는 모든 벡터에 이렇게 표시할 수 있거든요. 무슨 얘기 알겠죠, 그죠? 그러면 이게 지금 U 낫이라고. 그러면 AK를 곱했잖아요, 이렇게 AK를, 그죠? 솔루션 구할 적에 이게 뭐 UK라며, 그죠? 그러면 여기다 AK 다 곱한 거, AK에서 다 곱한 거거든. 그 AK에서 곱하면은 이제 뭐가 되느냐 이렇게 본 거거든요. 예? 그래서 봤더니 그래서 이제 보면은 이렇게 나오는데 U 낫을 각각의 벡터로 나타낼 수가 있다. 이렇게 멀티플라이 했더니 여기서 보면은 디컴포즈하면 바로 이퀘이션이 굉장히 쉽게 스텝 3처럼 무슨 뭐 나오더라는 겁니다. 그래서 U 낫을 그 아이겐 벡터로 디컴포즈 한 다음에 각각 풀면은 굉장히 일이 쉽게 되더라. 그게 기본 개념이에요. 그래서 이게 디퍼런스 이퀘이션을 쓸 적에 특히 이제 그 여러분 캐릭터리스틱 이퀘이션을 그냥 무조건 풀었지. 예를 들면 캐릭터리스틱 이퀘이션 뭐예요? 한번. 캐릭터리스틱 이퀘이션을 어떻게 풀었어? 기억나? 기억나니? 이렇게 하죠. 람다의 n 플러스 2. 람다 n도 다 지우다 보니까 람다는 나누지 뭐. 오케이. 람다 스퀘어 람다 플러스 1이네, 그지? 그래서 람다 스퀘어 마이너스 람다 마이너스 1. 이거 푼 거지. 아까 우리 저기 그 매트리스 구해놓고 A 마이너스 람다 지점인데 그거 똑같지, 그지? 오리진이 거기서 나온 거예요. 무슨 얘기 알겠지? 이건 외워서 해라 그랬잖아, 단지, 그냥. 무슨 말씀인지 아시겠지, 그지? 아, 이걸 보니까 왜 그 친구들이 이렇게 하라고 시켰구나 하는 게 감이 잡히잖아요, 그죠? 무슨 말씀인지 아시겠지, 그지? 오케이. 지금까지 한 가지 혹시 질문 있어요? 오케이. Let's move on differential equation. What's the difference between two? It's like a twin, right? So what's the difference between two? 이현경, can you tell me what's the difference between differential equation and also difference equation? What's the difference? Anybody can explain what's the difference between differential equation and difference equation? Okay. Difference equation is, we are talking sequence. Okay? Let's say this is, you may say, k's time, k plus 1's time. You can, it shouldn't be time, but it's okay. But whatever time, it's discrete, right? The sequence, like, okay, zeroth time, next time, next time, next time, this is more or less, you can count. Okay? Then difference equation is continuous time, continuous time. Okay? Difference is based on difference of a specific time. Okay? So that's the difference between two. Can you give me just one example of differential equation you learned in high school? Have you learned anything in high school? What's this? Whatever Newton's law. 자유낙하의 법칙. 중력 가속도? G, right? Then what's, okay, let's say, what's the V? T. Assuming V0 is 0. This is basically we are saying, okay, this is integral 0 to GT, right? Okay, then this is GT, right? Or you may say, what's the distance of dt? Right? This whatever square, right? This is, you can, there's an integral form, right? Or the other way you can say, okay, it's a Vt is a whatever, a difference of you say, okay, you can say then V, right? Vt. Just remove just t. Then, okay, this is dt, the distance, whatever is v, right? Then whatever dt is dv is what is whatever g. This is another way to represent these differential forms, right? This is the one you learned. So this is a case when you have two variables, two-dimensional. Okay, so dt du1 is -1, whatever these things. So this even here you can say, oh, I say this is a d1, d is I say it's u1. I say this is u2, right? You can do that way, right? Okay. So this is example of differential equations. So when differential equation, also this is equation form, This is more matrix form. You can represent it as matrix form. This is the way you can represent. Okay. Then same thing. So using eigenvalues, now actually solution you can define. Let me just give you simply describe. 전혀 안 배웠죠, 그죠? 그러니까 이렇게 좀 디퍼런스 이퀘이션 할 때는 우리가 항상 아는 게 람다가 있으면 람다 K의 텀이 나타났잖아요, 그죠? 예? 근데 이제 여기서는 람다 K의 텀이 아니고 미방에서 이게 람다 T라 이런 엑스포넨셜 텀으로 나타나요. 썸이 엑스포넨셜 텀. 근데 지금 수학을 전혀 안 했으니까 이걸 나타날 수가 없는데 한번 이렇게 물어볼게요. 아까 이제 디퍼런스 이퀘이션은 람다 값이 제로보다 작으면은 시간이 지나면 그 텀은 없어지지, 그죠? 아니, 좀 1보다 작으면, 그죠? 예? 한번 이게 물어봅시다. 요게 요 텀은 람다가 제로면 어떻게 돼요? 이 텀은 1이고 람다가 네거티브면은 t가 쭉 증가하면 시간이 지나면 람다가 마이너스면 어떻게 가요? 0으로 가고 람다가 무한대로 가죠, 그죠? 무한대로 가죠, 그죠? 그래서 이제 그것만 이해할 수밖에 없겠네, 지금 상황에서는. 이걸 좀 보세요. 보고서 시험에 냈는데 어떡하지? 예? 제가 자료 줄 테니까 한번 시험에 내라고 보시고 이쪽을 설명하기가 굉장히 쉽지가 않을 건데 선택해놨는데 혹시 여기까지 뭐 질문 있어요? 미방에 대해서 전혀 감이 없으니까. 예? 제가 여기 자료를 강의 안 하고 자료를 스캔해서 포스팅을 내일까지 할게요. 쭉 해서 미방을 읽어보세요. 그래서 아까 걸 이해하면 그냥 블라인드 따라가면 되니까 준비할 것 같은데 지금 강의해봤자 어려울 것 같네. 혹시 질문 있어요? 시험에 대해서 질문 있거나 뭐 있어요? 다음 시간에는 저희 마크업 매트릭스라는 걸 설명할게요. 오케이, 강의 끝냅시다.